Space itself is expanding, and that unfolding stretch rewrites every sense of distance and meaning. From galaxies drifting apart to the quiet acceleration of the cosmos, this growth is a framework for time, scale, and what infinity might mean. In the expanding void, we translate the science of the expanding universe into ideas you can feel, why every measurement matters, how the horizon shifts, and what it asks of our place in the cosmos. You'll walk away with a clearer map of the universe's growth and a fresh sense of how the void shapes our stories, our technology, and our sense of purpose. Origins of cosmic expansion. Cosmic expansion is built into the fabric of space-time by general relativity. The large-scale structure is described by the Friedmann-Lemaitre-Robertson-Walker framework, where the geometry of the universe is encoded in a scale factor that changes with time. In this view, galaxies drift apart not because they push each other through space, but because space itself stretches between them. Distances grow as the metric expands, even when objects retain their local motion. The growth depends on the energy content of the cosmos, including matter, radiation, and any energy that acts like a cosmological constant. The outcome is a dynamic, evolving stage on which cosmic history plays out, with the expansion rate leaving a trace in the patterns we observe. One key idea is that space began to expand dramatically during an early epoch known as inflation. Inflation posits a brief period of exponential growth driven by high-energy fields. This rapid swelling smooths the geometry of space and drives the flatness that we infer on large scales. It also stretches quantum fluctuations to cosmological scales, seeding tiny irregularities that later become galaxies and clusters. Observations provide the empirical backbone for the idea of expansion. The cosmic microwave background offers a snapshot of the early universe when photons last scattered before decoupling. Its near uniformity with minute temperature fluctuations encodes the initial seeds. Large-scale surveys reveal a cosmic web shaped by gravity acting on those seeds. Distant supernovae measurements indicate the expansion rate is not constant, hinting at a form of energy that permeates space. That energy is commonly modeled as dark energy, with the cosmological constant being the simplest representation. The presence of dark energy changes the destiny of expansion, leading to ongoing acceleration rather than a halt. Philosophically, the origins of expansion invite questions about the nature of space, time, and causality. The same equations that describe growth also imply that the fate of distant regions depends on energy content. If acceleration persists, some regions will drift beyond our observational horizon. Inflationary ideas raise further questions about initial conditions and possible connections to broader multiverse concepts. In practical terms, the origin story of cosmic expansion anchors models of structure formation and guides interpretation of data. Evidence for expansion. Distant galaxies show spectral lines shifted toward the red, and the amount of shift grows with distance, a pattern that points to continual recession rather than a static cosmos. This relationship is encapsulated in the idea that space itself expands. Nearby systems bound by gravity do not follow this trend. The implication is that, on large scales, the fabric of space stretches over time, carrying galaxies along with it as the universe grows. The cosmic microwave background acts as a fossil glow from a hot, dense early universe and carries the imprint of how space expanded to reach us. That glow is a nearly uniform sea of photons detected from every direction, with only faint hot and cold patches. Those tiny temperature fluctuations map the early layout of matter and the way acoustic waves carved patterns as the universe expanded. The spectrum is a near-perfect blackbody. The uniformity across the sky plus the tiny anisotropies argue for a rapid expansion from a hot, dense state and for a history in which distance measures grew over time. Observations of the CMB also set a standard ruler through the pattern of oscillations that tells us about the size of the sound horizon at the time of decoupling, revealing how rapidly space had stretched. Observations of type Ia supernovae provide a direct probe of how expansion has changed over time. Type I supernovae serve as standard candles. By comparing their intrinsic brightness with how bright they appear, scientists infer distances, and when these distances are plotted against redshift, the trend shows expansion continues and perhaps accelerates. This acceleration implies the presence of a repulsive component in the universe. The result aligns with models that include dark energy as a driver of expansion. Baryon acoustic oscillations provide a standard ruler for cosmology, imprinting a characteristic scale in the distribution of galaxies that helps map how the universe expanded. Measurements of galaxy clustering trace this scale across different epochs. Redshift space distortions and gravitational lensing further corroborate a history of widening distances, reinforcing the narrative of an expanding void whose growth rate changes with the cosmos's energy content. Taken together, these lines of evidence form a coherent portrait of expansion over cosmic time. They also guide our understanding of components like dark energy and the fate of the universe. Mechanisms driving expansion. The universe is expanding, and dark energy currently dominates the rate at which space itself grows. Observations of distant Type I supernovae, the imprint of the cosmic microwave background, and the distribution of galaxies all point to an accelerating expansion rather than a steady, decelerating one. Space is not a stage on which objects simply move. It is the fabric whose metric changes, causing distances between distant regions to increase over time. The current expansion rate, quantified by the Hubble constant, sits around 70 kilometers per second per megaparsec, with measurements converging from different observational paths. In practical terms, the scale factor of the universe increases, and that growth reshapes the future prospects for structures already formed and those that have yet to form. Within the standard cosmological model, expansion is governed by the Friedmann equations, which balance energy content with the geometry of space. The matter component, including dark and baryonic matter, dilutes as the cube of the scale factor, while radiation fades even faster. A small, nearly uniform curvature term can tilt the balance, but observations indicate space is very close to flat, so curvature plays only a minor role at late times. Dark energy, characterized by an equation of state parameter W equals P/ρ, behaves as a persistent form of energy with negative pressure. For a cosmological constant, W equals exactly -1, and its density remains nearly constant as the universe grows. When dark energy begins to dominate the energy budget, the expansion accelerates, making the growth of distances continue even as matter becomes sparser. Inflation represents a different mechanism that operated in the early universe, setting initial conditions rather than driving late-time acceleration. A brief, intense phase of expansion was powered by the potential energy of a scalar field, causing space to stretch by an enormous factor in a fleeting instant. This rapid growth solves the horizon and flatness problems and explains why distant regions share similar properties. Quantum fluctuations during inflation get amplified and later seed the large-scale structure we observe as galaxies and clusters. Although inflation belongs to the early universe, its core idea, that a field's energy can push space outward rapidly, illuminates how different energy forms can govern expansion. Beyond the standard picture, researchers explore alternative mechanisms and extensions. Some theories modify gravity on cosmic scales, aiming to reproduce acceleration without invoking a cosmological constant. Observations track not only distances but the growth rate of structure, testing whether gravity behaves as predicted by general relativity in the presence of evolving energy components. Gravitational wave standard sirens provide an independent way to map the expansion history by linking luminosity distance to redshift from events like neutron star mergers with electromagnetic counterparts. Ongoing and upcoming surveys aim to tighten constraints on the dark energy equation of state, probe whether W evolves over time, and test for subtle deviations that could hint at new physics. Together, these efforts keep refining our understanding of how the expanding void, the fabric of space itself, operates, and what that expansion might ultimately mean for the cosmos. Meaning and implications. Space itself is expanding, and observations show distant galaxies receding in all directions. A more complete description ties the recession velocity to distance into a dynamic picture where the expansion rate is encoded in a parameter commonly represented by a Hubble-like relationship, and the farther away an object is, the faster it appears to move away. The observable universe spans roughly 46 to 47 billion light-years in radius, a figure that grows as light has more time to reach us. Crucially, this expansion happens even though gravity binds much smaller systems locally. Galaxies and solar systems remain bound while the space between them stretches. Current measurements indicate the expansion rate is accelerating, a phenomenon attributed to dark energy that acts like a repulsive force on cosmological scales and is often modeled by a cosmological constant. Today, the expansion rate is commonly stated as roughly 70 kilometers per second per megaparsec, a figure that anchors the overall picture while remaining subject to refinement. This means the stage on which cosmic events unfold keeps changing, even as the actors within bound groups follow their own local rules. One consequence is that there is no central point of expansion in the universe. Space grows, not because something is moving through space at a universal speed, but because the fabric itself stretches. As a result, light from distant regions takes longer to arrive and, in some cases, may never arrive at all if those regions cross beyond the cosmological event horizon. Meanwhile, we observe more universe over time. The observable patch increases as time passes, yet there is a limit to how far future observations can reach. These features reshape what we mean by distance, turning it into a measure of our causal connectedness rather than a simple spatial coordinate. The expanding void also implies that new regions become accessible only through the slow advance of light and advance of time, a reminder that our view of the cosmos is always partial and provisional. Practically, expansion is baked into how we measure the cosmos. Standard candles and standard rulers anchor distance scales, and they reveal that the fabric of space is not static. Dark energy, often modeled as a constant energy density filling space, drives acceleration and changes how structures grow and how horizons evolve. Cosmologists lean on the lambda-CDM framework to reconcile expansion with the clumping of matter into galaxies and clusters. This model fits a wide range of observations, but leaves open questions about the true nature of dark energy. Over billions of years, this expansion dilutes matter and radiation, alters the rate at which galaxies form, and reshapes the future of cosmic structure. The practical upshot is that the universe behaves like a dynamic stage where timing, distance, and energy content all tilt the balance of what can influence what and when. From a human perspective, the expanding void invites a rethink of scale. It lifts us above a tightly bounded frame of reference and gives a sense of how tiny individual lives are within a vast, evolving cosmos. Meaning here is not a fixed doctrine, but a cultivated awareness. The universe is producing a future that we can influence only within our light cone. Scientists and thinkers draw practical implications, planning long-term missions, preserving knowledge, and probing the deep questions about why space exists and what form meaning might take amid increasing complexity. Ultimately, the expanding void becomes a mirror that both humbles and inspires, challenging us to care for what we can touch and to wonder about what lies beyond the horizon. Future prospects and cosmic fate. The expansion of the universe is accelerating, driven by a pervasive energy that fills empty space and acts against gravity in a subtle but relentless way. Distant galaxies drift away faster with time. As a result, the observable cosmos reveals a growing horizon beyond which events cannot influence us. Within our local group, gravity still rules. Over immense times, the chemistry of star-forming gas shifts toward exhaustion, and the glow of newborn stars fades as old stars burn out. The future looks quiet and cold. Scientists aim to test whether dark energy is truly constant or quietly evolving, because even a small shift could alter the fate of all cosmic structures. Upcoming surveys will sharpen clues. Projects like Euclid, the Roman Space Telescope, DESI, and the Vera-C Rubin Observatory are designed to track the expansion history, map gravity on vast scales, and reveal how light bends through the cosmic web. These efforts may confirm a cosmological constant or uncover hints of dynamic fields. If dark energy changes, new physics beyond the standard model could emerge, guiding us into a revised picture of space, time, and fate. With a true constant dark energy, the universe could settle into a cold, empty expanse where existing structures persist only as fossilized remnants, and the vast majority of matter drifts beyond the reach of any life. The Big Freeze is a quiet end. In that scenario, star formation halts on cosmic timescales, stars burn through their fuel, black holes dominate the long run, and entropy climbs toward a final equilibrium. Some futures entertain dramatic twists. If the energy density strengthens over time, a big rip could erase galaxies, solar systems, and perhaps atoms, sweeping the cosmos apart on timescales far beyond human history. Beyond equations and forecasts, the expanding void asks us to place our lives in a universe that grows increasingly distant and quiet, a thought that reframes meaning toward resilience, curiosity, and careful stewardship of finite resources. The long view invites collaboration. Even as the cosmos expands, advances in observation, propulsion concepts, and sustainable living could extend the practical reach of civilization, shaping how we think about travel, energy, and information across cosmic distances. Ultimately, fate may be written in the physics of energy and space, not in our wishes. That's our closing note for the expanding void. We've looked at space as a growing fabric rather than a static stage, at galaxies receding as the cosmos stretches, and at how that expansion reshapes our sense of scale and meaning. The observable universe may be finite for us, even if the whole cosmos is vaster still, and the sense we chase comes from curiosity, shared inquiry, and the stories we tell about our place in the vastness. If this brought up a thought or a question, first I'd love to hear it. Leave a comment, share your perspective, and tell me what you'd like to see next. If you enjoyed this, consider subscribing and turning on notifications so you don't miss future explorations. In the next episodes, we'll dive deeper into dark energy, the ultimate fate of expansion, and how scientists test these ideas with telescopes, gravitational waves, and large-scale surveys. Until then, keep looking up, stay curious, and remember, the expanding void is not just about distance. It's a doorway to our ongoing story.